Hello class, this is a video tutorial on the limiting sums of infinite sequences. If an infinite geometric sequence has a ratio absolute value r is less than 1, which pretty much means it's a fractional or decimal ratio, so 0.1, negative 1 over 8, negative 0.12, etc. So long as it doesn't have any whole values, so things that you can't do are like 1.1, can't do that, or negative 9 over 8 because that has one whole, or negative 2.12, can't do that either, or 6 over 5. So these are not fractional ratios as they have a whole component on them. So this limiting sum only works with decimal or fractional ratios. So if this is what we have, then the sum of all of its terms, even though it has an infinite number of terms, will be a constant. So for example, 8 plus 4 plus 2 plus 1 plus a half plus a quarter plus an eighth, an infinite number of times, it'll actually just be equal to 16. This addition of infinite terms is actually called a limiting sum. And to quickly calculate this, we use the formula s of infinity is equal to the first term a divided by 1 minus the common ratio r. And once again, as a reminder, this only works with the ratio being less than 1. So let's calculate the limiting sums of the following geometric progressions if they exist. So here's the first two examples, and here are the next two examples. So let's get to it. For this, we need the first term. It's very easy to see. It's 10,000. And the common ratio is any term, so let's pick the 1,000, divided by the previous term, 10,000. You can check in your calculator, or you can just do some zero cancelling. So 1, 2, 3, 1, 2, 3. Common ratio is 1/10. You can always double check. Next term is 100 divided by the previous term, which is 1,000. Cancelling off the two zeros, we're left with 1 over 10. So this will definitely work because our ratio is just 0.1, which is less than 1. So to find the limiting sum of s infinity, we get 10,000 divided by 1, which can leave it as a decimal. 1 over 10 is 0.1. Straight into our calculator for this. 10,000 divided by 1 minus 0.1. We actually get a recurring decimal, which is 11,111.1 recurring. So there we have it. Or you can leave it as a fraction, which is 100,000 over 9. Let's try it again for this. Let's leave my calculator open from now. Our first term is 36, and our ratio, negative 12 divided 36, gives us negative 1/3. And you can always double check that it's indeed the common ratio by checking the next term, 4 divided by negative 12. We also get negative 1/3. So the limiting sum, s infinity, is equal to the first term, 36, divided by 1 minus 1/3. That's a common error that students make because the formula is already 1 minus r, but the ratio is negative, so it's going to be 1 minus 1/3. Using a calculator, 1 minus negative 1/3. Whoops, it's not working. One more try. You know what I'll do? Divided by 1 minus negative a third. Need more space. There we go. Good. That's equal to 27. So I hope that's nice and simple enough. So I want you to go ahead and try with these two examples here. Again, let's find the first term. A is equal to 15. The common ratio is going to be, well, let's test it out. 153 over 10 divided by the previous term. Check that into the calculator. 153 divided 10 divided by 15. It's going to be 1.02. Now, I hope you caught that this actually will not have a limiting sum because it's going to go off into infinity. So since the ratio r is greater than 1, we can just say no limiting sum. Limit sum. But now if we wanted to find the actual sum for this, we can't ever do s infinity. We need to find a particular s of n, which has not been specified for this question. So all we can say is that there is no limiting sum for this question. Try it one more time. Here we go. A is equal to 12. The ratio, let's test it now, negative 21 divided by 12. And I hope you saw again this one's negative 1.75. If we take the absolute value of r, which is positive 175, that's greater than 1. So again, we can say that there is no limiting sum for this. The only sum that we can do is s of n, which we have done previously, but we now need to specify which term we want to add up to. So that's rather an anticlimactic ending, but I hope you saw that it's rather simple to utilize this limiting sum formula to find the infinite sum of a series which has a ratio which is less than 1. So, hope to see you in the next video. Best of luck.